Welcome back, college chemistry. Today we're going to continue our conversation with electron configuration. So I would write some things down. I'm going to go through some examples. We will probably implement this a little bit more and show you some visuals maybe in class. But this is the second part of the electron configuration, just some more details to kind of layer in or add to what we've been discussing. So the first thing to talk about here is there is a difference between what we call orbital diagrams and electron configuration. And so I thought I would just kind of show you an example of oxygen. Oxygen has 8 electrons. And so if we were to kind of think about where those electrons are, typically we start with this right here, 1s. We can put 2 electrons in, right? So we draw these up and down. Then we would move on after the 1s, since you can only fit 2, you move on to the 2s, you put 1 up, 1 down. And then when you get to the next section, we have 3 separate orbitals for 2p. So p being the sublevel within that second energy level, so s and p. And then since we have, 4 more to go, we would go 1 up in each of these 3 before we go back and pair them up. Remember Hund's rule. And then our 8th one would go right there. Okay, this right here, what we are looking at, this is called the orbital diagram. And the difference between orbital diagram and electron configuration, once you get the orbital diagram, then it's pretty easy to go to electron configuration. The electron configuration is when we say, okay, how many do I have in the 1s? I have 2. So I put the 1s2 there, and then we move on. How many do we have in the 2s? 2. And then we move on. In the 2p, we count there's 4 of them. So we write 2p4. This is the electron configuration. Okay. Now, electron configuration tells us quite a bit of information. However, this orbital diagram actually gives us a little bit more information. It shows us really where each electron is located. And if you look closely there, we can tell that, hey, in the case of 2p, we have 2 electrons in the first orbital. We only have 1 in the second and 1 in the third. This 2p4 right there doesn't really tell you that. And so you have to know a little bit more about the orbital diagrams and what the orbitals look like to be able to kind of get that information. So that's why a lot of times this orbital diagram picture drawing out, excuse me, the lines and where the electrons go. Sometimes it's really more helpful information, and I will come back to that toward the end of this video, okay, and show you why sometimes it's better to have that. All right, the periodic table, this is really, really, really important. There is a shortcut for you to understand how to use your periodic table for electron configuration, okay? First things first, when we are looking at the periodic table, excuse me, we're talking about the electrons. We're talking about the last one in. So for instance, for oxygen, yeah, there's 8 electrons for oxygen, but we're talking about the 8th electron. And so we associate that with, hey, that's oxygen's electron. And then the 9th one would be fluorine, because there's 9 electrons. And so we associate the last electron with that particular element. Okay, in terms of big picture periodic table, here's what you need to know. First of all, this section right here, the first 2 columns, and also helium. Helium fits in a little bit better over here. This is called the S block on the periodic table. And again, you may already know this. This might just be review. That section right there, when we are putting electrons in, we are putting them in the S sublevel. Okay. This section right here on the periodic table, again, not including helium, because helium really fits over on that other side. This is called the P block of the periodic table. So when we're putting electrons in, for instance, we just did oxygen, the electron, the 8th electron, that fell in the P block of the periodic table, right? This middle section of the periodic table right here, this is the D block of the periodic table. And then this, these little rows that are pulled out below, and they actually fit in right here. This is the F block on the periodic table, okay? Now, some other things that might be helpful to you in terms of knowing this is that, I'm going to kind of change color here, is that the first row right here, right? Hydrogen and helium, that would be where we would be filling out 1s. So this is really like the first electron would be the S1 electron, the second column over S2. Okay, so even thinking down to like sodium, that first column, that is an S1 electron, and then magnesium, next one over that, you're putting S2 there. If we were to kind of number these all the way down in terms of rows, it actually tells you which S we're talking about. So the first row, hey, that's 1s. The second row with lithium and beryllium, that's 2s. Sodium is 3, excuse me, 3s. Potassium 4s, rubidium 5s, and so on. So what that does is it really makes an idea here, let's say calcium, that based on its location on the periodic table, you know that calcium is going to end with 4s, and then since it's in the second column, 2. And you could fill in everything before it, but that last part, based on its location, you could know, which makes your life a little easier, okay? And I'll go through some more examples here in a minute. In the P sublevel, those numbers hold true also. So this, for instance, is 2P, 3P, and then gallium would be 4P, and so on. What's different, though, what's interesting, you should already know this from in order. We go 1s, we fill that up, then we fill up the 2s, then we fill up 2P. So I go this direction, right? And then 2s, and then 2P we fill up, and then 3s, and then 3P, right? And then you move on to 4s. This next section, when we finally hit D, this is actually 3D right here. You're down 1 energy level. Why? Because remember, the third energy level can have S, P, and D, but the 4s has just a little bit less energy associated with those electrons. So we actually put some in the 4s, and then we go back to the third energy level and fill in 3D, and this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So all the way up to 3D, 10 as we fill them all the way across. So then the next row down, that's 4D, 5D, and 6D, right? So if we're filling up electrons after 4s, we go 3D, and then we go back. This is 4P, we fill that out, right? And then 5s, and then 4D is filled out, and then we get to 5P, and then we move on to 6s. Now, this is interesting. We take a detour. Okay, we move down here. This is actually 4F and 5F down here. So the fourth energy level is the first place we get a sublevel of F. And so these are, if you count how many of them there are, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14, right? So we can have 4F all the way up to 14. After you get through with filling 4F, we come back and we go 5D, 1 through 10, and then we go 6P all the way across, 1 through 6, 7S, take a detour again, we go 5F all the way through 1 through 14, and then we come back up 6D all the way through 1 through 10, and then 7P is all right here, right? Now, good news, we won't spend a lot of time with the F sublevel, okay? We will do a little bit of that, but one of the probably the biggest things you need to catch is what to do in terms of, especially in the D sublevel. So let me run through a couple just quick examples with you. Let's say we wanted to do the electron configuration for, oh, I don't know, let's do zinc, okay? If you look at zinc on the periodic table, if we were to try to go through and write electron configuration from the periodic table, since you know this is 1, 2, 3, 4, 5, 6, 7. This is the S sublevel, P sublevel, D sublevel, right? This right here is 3D, so on. So here's what we could do is we could say, okay, well, the first thing I'm going to do, hydrogen, helium, okay, that's 1s2. Then we move on, lithium, beryllium, that's 2s2. Back up a little bit. How many electrons are we going to? Hey, we're going to 30 electrons, right? So after 1s2, 2s2, we move on to 2p, and we put 6 of them in there, right? And then we move on to 3s. I'm going to just go down below, even though I'd write this probably in a straight line. 3s, there's two of them, right? And then we go on to 3p. So there's 3p6. And then we move on to 4s. We can put two of them in there, 4s2. And then we are finally into the section where we find zinc. And so we could just count them and go 1, 2, 3, 4, 5, 6, 7, 8, 9. Hey, I'm on the last one anyway. So 3d10. That is your electron configuration for zinc. So you can pretty quickly find and locate the element, and it actually tells you very quickly. We would know based on its location, we know that it ends in 3d10, and you can fill in everything up to it. So knowing the periodic table and how it's arranged will really help you with electron configuration. Okay. All right. Now, moving on, we got a couple more things to talk about. Shortcuts. You guys all like shortcuts, I'm sure. So let me show you the shortcut. The shortcut is called noble gas or core notation. Okay. If we were to deal with phosphorus based on the periodic table, we've got 15 electrons. You could follow that same process, 1s2, 2s2, 2p6, right? Hey, I'm up to 10. 3s2, and then we go 3p3. That's a total of 15 electrons. Now, looking at what we have here, one thing to kind of point out, we've got 2 electrons in the first energy level, 8 in the second, because the 2 and the 6 added together give me 8. Third energy level, we have 2 plus 3. Hey, that's 5. This last energy level, these are called valence electrons, because they're in the highermost energy level of that particular element. So these are called valence electrons, okay? The ones in lower energy levels, these are called core electrons, okay? Now, this shortcut basically is taking the core electrons and doing something very simple, is figuring out, okay, what element represents that core amount of electrons, 2 plus 2 plus 6, hey, that's 10. So our neon is a noble gas. So we write neon and we put brackets around it. And then the valence electrons gets tacked on at the end. 3s2, 3p3. So this is the shortcut. We call it core notation or noble gas configuration. Sometimes it's not really saving you a whole lot like on that one, but look at this next one. I've got polonium, okay? Polonium has 84 electrons, and you guys would be very frustrated if we had to start from scratch and write 1s2, 2s2, 2p6, and so on. Here's what we can do. We locate polonium on the periodic table. It's the 84th element. You locate then the noble gas on the line before it, and if you look at a periodic table, you will find that xenon is the noble gas before it, which represents 54 electrons. That, putting xenon in brackets, says, hey, everything that we have for xenon, 54 electrons, and then we tack on after that. So you have to go to xenon, the noble gas before, and then you go to the next line, and it looks like we're at 6s, where cesium is, and I know I can put 2 of them in there. Now I'm up to 56 electrons. Again, when you get to 57, we have to take the detour. We go down to 4F and we put 14 of them in there. And how do we know where we are at this point? Well, the last one there in 4F is 71, element number 71. And then we come back up to, remember, 5D is, remember, D is always 1 behind. So 5D, and we can put 10 of them in there. And then once we get to the end of 5D, I'm at 80. That is mercury. So if I stop there, I have the electron configuration of mercury, and I have 1, 2, 3, 4 more to go. Where do I put those? I put those in 6p, so 6p4. Okay, now on that one, core notation is huge in terms of saving you some trouble. Okay, now I know the question you're going to have. If I say, hey, give me the electron configuration of xenon, can I just put xenon in brackets? You cannot. By definition, this shortcut, this core notation, you've got to go with the noble gas before it. So I would look up xenon and I would go, hey, that's element 54. The line before it is krypton is the noble gas. So I put Kr, and then I tack on 5s2 See where I am, 5s2, 4d10, and then I have 1, 2, 3, 4, 5, 6. So 5p6. The whole point of the core notation is to really kind of show the last part of the electron configuration, so that if we wanted to look at how many valence electrons, like in this last one here, there are technically 8 valence electrons because 5s2 and 5p6, those are both part of the 5th energy level, the outermost energy level, right? Polonium, right before it, we have 6s and 6p. So we have a total of 6 valence electrons, right? So we're going to talk a little bit on the next section here on the importance of knowing where your valence electrons are. So let me clear this and we're going to move on kind of to the next section. All right, the next thing we need to talk about is ions. Ions are a little bit tricky when it comes to electron configuration. One of the important rules you need to catch is that when we are dealing with positive ions and you are removing electrons, you have to remove valence electrons, which are the outermost energy level, first. Okay, give you a quick example. Here with iron, let's do the shortcut. Since iron is the 26th element, what I would do is I would go to argon, the line before, which represents 18 of them. And then I would move on to 4th energy level, 4s2, 3d, and then we would count 1, 2, 3, 4, 5, 6, 3d6, right? That would represent the electron configuration for an iron atom. Now, if we look at the next example here, we're going to lose 2 electrons when it becomes Fe2+. Really important thing to catch. You cannot miss this. We have to look back and go, where are my valence electrons? Because we have to take those away first. 4s2 are my valence electrons. They are the highermost energy level. So we have to remove from them first. So if I'm going to just remove 2 of them, 4s2 actually goes away. So I can still keep my argon, but then I'm going to skip 4s2 because those just went away and I only have my 3d6. So if you're counting electrons, this argon represents 18, 18 plus 6, hey, I'm down to 24. So the 4s2 went really to 4s0. You don't have to show that. You can just erase, get rid of it. But that is really important for you to catch, that our valence electrons go away first. Well, what if we had more electrons we wanted to take away from iron? Let's say we were losing a total of 3 electrons. Well, you would lose the 4s2 first. Where would you go after that? You would go to the last place of the 3rd energy level you put them in. And so this one would turn into argon 3d5. So the third, so you would lose 4s2 goes to 0 first, and then you would take your 3d6 down to 3d5. That's where the 3rd one comes from. All right, let me give you one more example. Chromium 3+, we're going to lose a total of 3 electrons. Here's what's really important. I would suggest you start with neutral chromium, which has 24 electrons, because you need to kind of see what the neutral looks like when you're removing, so you know where to remove them from. So I'm going to write out chromium, which again, we're going to start with argon, and then I'm going to tack on this 4s2, 3d, 1, 2, 3, 4. Okay. Now, if I want to get rid of valence electrons, I've got to lose 3 of them. The first 2 I'm going to lose are these. Okay. And then the 3rd one I'm going to lose is this. So our new, for the ion, we're going to take argon, and then we're going to have 3d3. This is what Cr3+ looks like. I think it's important that you write out the neutral first before you try to remove the electrons. I think it's essential that you see it so you can kind of identify that you had 2 in the outermost energy level that had to go away first. All right, now to go back to, let's deal with another ion, bromine, Br1-. Normally bromium or a bromine atom has 35 electrons, but we are gaining an electron. So we are gain one electron from the neutral. Here's the good news. This is super easy. You don't have to do anything other than add up your 36. We have 36 electrons. So we can go to argon, and then we're going to keep going till we get up to 36. So we have argon, 4s2, 3d10. Hey, I'm at where zinc is, so I'm at 30, and then I continue 4p. Normally you would be 4p5, but we just gained one, so we're actually 4p6. This is the same as krypton, right? Because the bromine, when it gains an electron, it becomes just like the noble gas right after. So they actually share the same electron configuration. So there's nothing strange about adding electrons. It's really all about the losing electrons. You have to lose the outermost energy level first, and that's a little bit goofy. All right, let's see what other thing. One last detail, and we're going to talk about this in a little bit more detail in class because this is a little bit confusing. We're talking about two terms, paramagnetic and diamagnetic. Here's what you need to know. Paramagnetic means there's an attraction to a magnetic field due to unpaired electrons. Unpaired electrons is what's causing this. Okay, so anytime we have electrons that are not paired up, you can have some attraction to a magnetic field. Diamagnetic, there's no attraction to a magnetic field. It's because all the electrons are paired up. So here's what you have to do is if I wanted to look at oxygen, and I would go back to the electron configuration of oxygen, 1s2, 2s2, 2p4. It's hard to tell whether or not those electrons are all paired up or not, right? So what we do is we typically take the last part of the electron configuration and we go back to orbital diagrams and we see what this looks like. So 2p4, remember there's 3 p orbitals. So I go 1, 2, 3, and then I put my fourth one there. If you look closely here, I have 2 electrons that are unpaired. Because we have unpaired electrons, we would call this paramagnetic. And what that means is if I put a magnetic field near oxygen atoms, a sample of oxygen atoms, I should have some attraction to that magnetic field. There's kind of some magnetic properties that would come along with that because of those unpaired electrons. All right, let's look at an example of neon. Let's see whether that's true or not. So neon is very similar to oxygen, but I have 2 more electrons. So 1s2, 2s2, 2p6. And again, using that orbital diagram to evaluate 1, 2, 3, 4, 5, 6. Hey, look, these are all paired up. So we have all paired electrons. Okay, so what we would say is that these are diamagnetic. So we would not expect magnetic properties. So if you put a sample of neon in a magnetic field, it's not going to have any kind of attraction to that magnetic field. All right, 2 more quick examples here, just so you can kind of see this again, how we would do this. And I'm going to do a couple of these. We're going to show you some in class with a demo. Iron has 26 electrons, so we go with a shortcut, argon, and then 4s2, 3d, 1, 2, 3, 4, 5, 6. I'm just counting with my periodic table. Remember, there's 5 d orbitals in the 3d, and we have 1, 2, 3, 4, 5, 6. So, hey, do we have unpaired electrons? Absolutely. If we look closely here with unpaired electrons, these are all unpaired, and therefore we would call this paramagnetic. What does that mean? That means iron has some very strong magnetic properties because of these unpaired electrons. And we'll show you that a little bit in class. Let me do one more example with you with cobalt 3-. We'll go through the same process. Remember, we have to go to the neutral cobalt first before we remove. So we'll go with argon, 4s2, 3d, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7 is what neutral cobalt would look like. So if I want to go cobalt 2 plus, sorry, it's 3 plus, isn't it? Cobalt 3 plus, let me erase that. We have to lose the 4s2 goes away, right? So this goes away and this goes down to 6. So we have 3d6. So we would draw out our 3d sublevel and we would go 1, 2, 3, 4, 5, and there's our 6, 1. So we would definitely say that this is paramagnetic. So the key thing here is you're looking for, do you have unpaired electrons or not? If you do have some that are unpaired, doesn't matter how many, as long as there's one or more unpaired, you would call it paramagnetic. If all of them are paired up, you would call it diamagnetic. All right.